It is one of the most abundant materials on our planet, yet it holds the key to the ultimate high-tech future: quartz. The journey begins at Factory A. A heavy-duty truck arrives, hauling tons of high-purity quartz.
From the deep bunkers, automated conveyor belts transport the stones up into a high-capacity weighing station.
The crane operator moves the raw mixture toward a machine that mimics the fiery core of the electric arc furnace.
Inside this artificial hellscape, a violent chemical divorce takes place. The carbon strips the oxygen away from the quartz.
A technician breaks the furnace tap, releasing a torrent of liquid silicon at nearly 2,000 degrees. Once cooled, To make a solar cell work, the silicon must achieve a level of purity that borders on the miraculous. The crushed silicon. The reaction creates a volatile, boiling liquid compound called trichlorosilane. This constituents. The purified gas is pumped into a vacuum chamber containing thin, glowing silicon starter filaments, heated to over 1,000. When the chamber cools, technicians harvest rods of polysilicon. This is now electronic-grade silicon. This process is called doping. The boron gives the silicon a positive electrical charge, turning it into what engineers call p-deposits. A mechanical hoist lowers a single crystal silicon seed into the molten pool. The mechanism begins to rotate, pulling the seed upwards. As the liquid cools against the seed, the atoms lock into a flawless, continuous crystal lattice. The result is The rounded ingot is square-shaped by industrial saws, then moved to a high-speed multi-wire cutting machine. In a single, continuous slice, the wires cut the block into hundreds of ultra-thin squares called wafers. The wafers are thin and clean, but their surfaces are still too smooth. They reflect light like a mirror. To fix this, the chemical etch textures the surface, creating millions of microscopic pyramids. When sunlight hits the wafer, the light melts. Now comes the moment where the wafer gains its electrical power. The P-type wafers travel through a furnace filled with high-temperature phosphorus. Where the positive boron layer meets the negative phosphorus layer, an invisible, permanent electrical barrier is born. To maximize light absorption, the wafers enter a vacuum chamber where a brilliant blue layer of silicon nitride anti-reflection coating is applied.
A final blast of heat fuses the metal lines directly into the silicon crystal structure, creating the conduits that will carry the electricity away.
The manufacturing is complete. A solar simulator fires a high-intensity flash of artificial sunlight at the cell.